Okay, so I'm going to take us even further out. So we've heard about mature galaxies, adolescent galaxies, teen galaxies. I'm going to talk about toddler galaxies. And so the universe is 13.7 billion years old. And in defining the early universe, which was the task I was given, I've chosen the first billion years of cosmic history. So that's the first 7% of the age of the universe. And I've just had 2 grandchildren, and I can tell you the toddlers are definitely the most interesting part of the cosmic history. So Keck is just a fabulous time machine. A number of people have emphasized its utility, and I like just in this slide to just illustrate how we directly witness the past. So think of astronomers as archaeologists. Here are 2 nearby galaxies, this smooth elliptical galaxy and this spiral galaxy very similar to our own Milky Way. And I think the wonder of Hubble, of course, is that we see pictures of galaxies out in great distance. And so here, when the universe was 5 billion years old, you can see the beginnings of the morphology that we see in the local universe. So this galaxy here and this one here, they're not quite as well formed as the spiral galaxies that we see today, but they're certainly reminiscent with a central bulge, and you can see the beginnings of spiral structure. These 2 galaxies here look like early versions of the elliptical galaxy. If you go to when the universe was 2 to 3 billion years old, then the galaxies become very different. They're very small physically, and their morphologies are not yet clear. Many of them could be merging, or they may have star formation regions that are relatively clumpy. But here in one picture, you see piecing together the cosmic history. And the key ingredient, as several speakers have emphasized, in making this time slice is the redshift. And in fact, if you have very good eyesight, the redshift of the galaxies are shown in the upper panel here. They're about a redshift of 1 or so. Now I'm going to talk about much earlier galaxies than even these galaxies here, which correspond to a redshift of 3 or so. And I think it's amusing not only to be archaeologists, but also to be historians. And let's go back to 1985, when a very important document was written called the Blue Book. And the Blue Book, the Keck Blue Book, is in a sense a blueprint not only for the technical construction of the Keck telescope, but also the scientific case. And the frontier in 1985 was very much Redshift One. The synergy with the Hubble Space Telescope was recognized, but here's an interesting paragraph from that Blue Book. Distant galaxies at a Redshift 1, whose light was emitted when the universe was only a third its present age, can be certainly detected with existing telescopes. Existing telescopes at this time is 4-meter class telescopes. However, a major datum is the distance. For this, we need the spectrum so that we can time slice the universe. This needs a large telescope, and this will be a major area of research for what was then the 10-meter telescope, later the Keck telescope. So this panel here just shows the most distant published object, right or wrong, against time, okay, for quasars, galaxies, both radio galaxies and optical galaxies, and these Johnny-come-latelys called GRBs, which Professor Kulkarni is so enamored with. And you can see that when the science case for Keck was made, there weren't any measurements for GRBs. Quasars were already known. A lot of the high redshift quasars were published using Palomar and the Anglo-Australian telescope and the Lick Observatory. And then when Keck switched on, you can see basically we were at around a redshift of 4 or so. And now we're about at a redshift of 7. And with this new instrument, MOSFIRE, we have the great potential to go to even earlier times. So there's a tremendous progress. And I think the first big step forward with Keck was made by Chuck Steidel, and he was very modest in not mentioning this in great detail in his talk. But how do we find a distant galaxy? It's very dangerous to assume that a faint object is very distant. Galaxies have a wide range of luminosity, and so a faint object could be an intrinsically feeble object really quite close by. So you need some other information before you embark on spectroscopy of very early galaxies. And the trick is that the hydrogen in the atmospheres of the stars in a galaxy, in the interstellar gas in the galaxy, and along the line of sight in cool clouds of hydrogen, such as Jason X-Prochaska told us about in his talk, extinguish the light of a galaxy in the ultraviolet. And so if you image an area of sky in a red filter, a green filter, and an ultraviolet filter, most of the galaxies that are close by are seen in all three filters. But this circled object here disappears in the shortest wavelength filter. This phenomenon has been known as a dropout. Most parents don't like that word, but this has become the nominal term for this technique, which screens the most distant objects, pre-selects them using their color. And so Chuck used this to open up the high redshift universe in one of the first early publications from Keck in the mid-90s to find galaxies at a redshifts of 2 to 3 or so. But the technique is very versatile. Any three combination of filters can be chosen. So we could shift these filters to longer wavelengths and use the same technique to get higher redshift galaxies. So let's leap forward to 2003. And here, with a 5-hour spectrum from Deimos, is a galaxy at a redshift of 6. And this was sufficiently exciting at the time that a paper was based on one object. So the reason is it was detected both by Hubble and by Spitzer, so we could measure its redshift from this hydrogen emission line, which is Lyman alpha, which you've already been introduced to, and the Spitzer measurements actually measured the age of the stars in that galaxy. So even at a time when the universe was only 7% of its present age, about 1 billion years old, we knew that that galaxy was not a latecomer. It had already been forming stars for quite some time. From one object, and I think this is just the tremendous progress that we've made with multi-object spectrographs, we have now done a survey of over 600 galaxies beyond a redshift of 3.5 or so, using initially Deimos, but now with the red-sensitive CCD on low-res, we've pushed this out to redshift 7, and I'll show you some more information on this in a minute. And I like very much this plot because this shows the galaxies that drop out in the B filter and their redshift distribution, the galaxies that drop out in the V filter and the I filter, and it also shows those terrible European competitors and how Keck has really dominated. I say this, of course, with a British accent, how the Keck telescope has dominated the redshift survey in this area. And also these form the basis of student theses, which I think is another unique aspect of Keck. So we're pushing Keck to the limit at redshift 6. We have almost 100 galaxies at redshift 6. And these are very ambitious exposures, typically 2 nights with Deimos or low-res. Here are some emission lines of Lyman alpha with the redshift indicated. You can see the line is very prominent. And typically we find over half the galaxies at this redshift show this prominent hydrogen line. So what is this hydrogen line? It's hot gas in the galaxy heated by young stars. So we're seeing galaxies 1 billion years after the Big Bang energetically producing stars. This is a very formative period of cosmic history. And the signature of this activity is the prominence of this hydrogen line. We've gone beyond, as have many other groups in partnership with Subaru. And I show here, because I think the partnership with Subaru has been particularly effective. There are 6 galaxies now published beyond a redshift of 7 in the last 3 years or so. 4 out of these 6 are from Keck. And the 3 most distant galaxies have been located using narrowband imaging with Subaru, so a filter that images the sky in this particular narrow line at a particular redshift, and then the confirmation spectrum comes either from DMOS, and this is I think this is just fabulous use of DMOS. This is right out at the edge of DMOS at a redshift of 7.2. This currently the most distant confirmed object at 7.3 from NIRSpec. And we're now looking at the universe when it was about 6% of its present age. Now, the media love record breakers, and no matter how you write the scientific paper with these kind of objects, with the astrophysics and everything, when the press releases come out, the journalists only seem to want to know about the how much further is this object than this object, and how much earlier in cosmic history. I want to now basically say that there's a huge amount of physics and in this particular first billion years of cosmic history. This is now in many ways the last uncharted period of cosmic history. So let me talk you through it. The universe began with a Big Bang. 300,000 years later, we see the glow from the Big Bang in the microwave background. So that's a very important moment in history when the hydrogen atom first forms. We then enter a period which is ominously called the cosmic dark ages. No stars, no galaxies, just hydrogen clumping under gravity. As these clumps of hydrogen cool and collapse, they eventually ignite in their cores and form stars and galaxies. And then there's a process which reionizes the universe, heats up the hydrogen in space and breaks it apart. And I'll describe that in more detail in a moment. So the questions at the frontier are always really remarkably simple, and that's in some ways the attraction, as Sri, I think, emphasized, of being bold and going into the frontier. When did the very first galaxies form? We call this moment cosmic dawn. What were those galaxies like? Did any of those galaxies, can we see those galaxies as relics in the local group, as Marla Geher described in her talk? Were these galaxies the only agent that broke apart the hydrogen in deep space? Let's start with the Big Bang. You may think, goodness, can Keck say anything about the Big Bang? You bet. Not the Big Bang itself, but the immediate aftermath of the Big Bang. We already heard from Keck's pioneering role in estimating the abundance of deuterium, arguably one of the most impressive results in the 20 years of Keck, in nailing down the exact amount of the material that makes up you and me. We're going to hear in a minute of Keck's leadership in the dark energy that is an important, if not dominant, component of the energy density of the universe, the accelerating universe, still a big mystery. But let's not forget, there's one other big mystery, and that's dark matter. Dark matter actually distills from the Big Bang at a very early stage also. It's not material like that makes up you and me. And it's the gravitational pull of dark matter that dominates the growth of structure, produces galaxies, clusters of galaxies, and everything that we see around us. So how do we probe dark matter with the Keck telescope? You can't see it. It doesn't even absorb radiation. So the only way that you can detect dark matter is through its gravitational influence. Yes, okay, you can buy it. These are two aficionados of gravitational lensing. This gentleman probably needs no introduction. He basically, of course, predicted that light is deflected by material. Curiously, he never really imagined it would have any practical purpose. Apart from the verification at an eclipse in 1919, Einstein and Eddington, neither of them really imagined that lensing would have much use other than verifying the elegant theory of relativity. Fritz Zwicky, a rather typical Caltech professor, one might imagine, had basically the insight in 1936 to say, one day, people will image the dark matter through this gravitational lensing effect. Here's a cluster of galaxies taken with the Hubble Space Telescope. You see these huge distorted features. These are distant galaxies well beyond the foreground gravitational structure of this cluster of galaxies that are distorted and magnified by this foreground structure. So Keck has exploited gravitational lensing in a beautiful way to determine the amount of dark matter and its distribution on small scales with a very interesting twist in the story which may or may not develop as we get more data. How much dark matter? Imagine you're at the bottom of a swimming pool and you look at the sky through the water in the swimming pool. The water in the swimming pool is rippling the structure that you see in the sky. Dark matter is everywhere in the universe. You look to the great depths of the universe and you see the night sky, and heaven forbid, it's not the true night sky. It's like wearing spectacles, but you didn't know it. Okay? The night sky is ever so slightly distorted by dark matter. And this we call weak lensing, and what you see is around structures, which are shown in white here, galaxies are stretched. The background galaxies, imagined as wallpaper, is stretched in its shape. And remarkably, in a very unusual use of Keck, actually, but I think very insightful, ESI, which had the best image quality of all the Keck optical instruments, was used in imaging mode over almost 200 fields in conjunction with a wide-field telescope, the William Herschel telescope, which didn't have as good image quality, to detect this cosmic shear. And what you see is the clustering of galaxies that are aligned in a similar way as a function of their separation. And the little dotted line here shows the best fit to the data. This is very early data, compared to a universe which is full of dark matter. And the ratio of these curves tells you how much dark matter there is. So this is one of the pioneering observations done in imaging mode with Keck. Is the dark matter cold? Sandy introduced the cold dark matter picture. It's been extraordinarily successful in explaining the distribution of matter and galaxies on large scales. One of the key tests of the cold dark matter picture, the cold dark matter is thought to be a massive elementary particle. We haven't yet found it. But its key prediction is that every galaxy, be it small or large, has a density profile that rises to a cusp in the center of the galaxy. So the dark matter density against radius rises very, very steeply in the inside here. This is known by three theorists who first determined this from cold dark matter simulations. It's known as the Navarro-Franken-White profile. Here's Navarro, here's Frank, and here's White, conveniently arranged in a profile. So dark matter can be tested with Keck. So in this case, it's spectroscopy. So here's a giant galaxy, and you can see it's producing these distorted images. We measure the redshifts of all of these images and their positions, and that tells us the geometry of the lens, and hence how much total mass there is that produces this distortion. We put a slit through the center of the galaxy, and we measure the motions of the stars and compare that with the size of the galaxy and its light profile, and that allows us to separate the normal baryons, the stuff that makes up you and me, from the dark matter. And what you see is that, and this is the average of 7 clusters of galaxies from Drew Newman's thesis, that the dark matter profile does not agree with the cold dark matter picture. And this is the case also in small independent evidence on smaller scales. Now, there are two possibilities. One is that the mode in which the galaxy assembles is not well understood, and earlier accretions of material may puff up the dark matter so it becomes flatter than the cold dark matter picture. And so this is telling us something then about the assembly history of these particular galaxies. But it's also possible that dark matter is not completely cold. It could interact and have a scattering cross-section, which would not affect in any way the properties of cold dark matter on large scales, but will resolve many of the interesting problems that we find on small scales. So let me turn to cosmic dawn and reionization, which comes after the Big Bang. It's unfortunate, but we live in a world where there are theorists. And this is a theoretical view from the most distinguished theorist working in this area, Professor Avi Loeb of Harvard University. And you can see the dark ages here. There are galaxies, little baby galaxies. They form stars. These stars heat up the gas. They produce these ionized bubbles. These ionized bubbles overlap, and we go from a neutral hydrogen, remember, proton plus electron, to an ionized gas, proton and electron split apart. So the theme is that early galaxies produced this ionization. And, the aficionados say it's somewhere between 200 and 800 million years after the Big Bang, redshift 6 to 20. So how can we test this? One of the first indications came from Keck with quasars. So you've seen this in X's talk. Here's how a quasar is used to illuminate hydrogen clouds along the line of sight to the telescope. And it's this Lyman alpha forest which measures cold amounts of neutral gas. So a number of groups, but I think Xiaoyi Fen at the University of Arizona probably has spent more time on this at Keck than anybody else, looking at the spectra of quasars from redshift 5.7 to 6.4. And if you look at this one here, you can see here's where the hydrogen absorption along the line of sight to the quasar would be, and there's a sort of little bit of noise here. But as you go further up, if you have very good eyesight, you can see it's like, a trace, that's completely flat where, somebody's passed away or something. It's just horizontal, nothing happening there at all. And so you can convert that into how much neutral hydrogen there is along the line of sight. And there's just this amazing hint that it's turning up as if we're entering the period where we have neutral gas everywhere in the intergalactic medium. Unfortunately, I haven't put a numerical scale on here, but this test is not that sensitive. So we need another test. And the other test uses galaxies. Unfortunately, we can't seem to find many quasars beyond a redshift 7. There's only one. But we're beginning to find large numbers of galaxies beyond a redshift of 7. And the hydrogen line of Lyman alpha is also a test of neutrality in the intervening space. So if you're sitting in an ionized bubble, the Lyman alpha line will escape. But if the galaxy is completely in a neutral area, you won't see the hydrogen line at all. It becomes immediately absorbed. So the analogy I like to use here is that it's a bit like looking at the freeway. You're looking back in time along the freeway to more and more distant objects. Each galaxy is an automobile, and the hydrogen line is the headlamp, the headlight. And you can think of the neutral era, the dark ages, as a fog. And the question is, when do you enter this foggy era? Well, Hubble launched this fabulous infrared camera in 2009, the Wide Field Camera 3. We now have even deeper images than the ultra-deep field in the infrared. And we now have a catalog of 74 galaxies out to redshifts of 10, in fact. This is just their distribution. And so we've started looking at the Lyman alpha visibility in all of these galaxies. So far we've looked at 24 of these galaxies. And you can see the fraction of them that show Lyman alpha this is just tentative at the moment, seems to be turning down as we go beyond a redshift of 7 or so. And in fact, here's another one of the Keck objects beyond a redshift of 7. And MOSFIRE, of course, will allow us to do this not one at a time, as Ian McLean emphasized yesterday, but 45 objects at a time. And so this is just going to be an enormous leap forward in capability in testing when reionization ended. And then finally, back to gravitational lensing. Lensing is fabulous because not only does it tell you about dark matter, but turn it around and say, I'm not interested in the dark matter in the foreground, I'm interested in the background galaxy. Gravitational lensing magnifies that background galaxy. It's like having a telephoto lens on the Keck telescope. And so here's a cluster of galaxies. So, there's a real opportunity to individually examine very distant objects. So in my final couple of slides, we just heard a couple of months ago that the Hubble Space Telescope, the current director, Matt Mountain, who many of you know, is going to invest many hundreds of orbits of Hubble time, of his director's discretionary time, to look at clusters of galaxies purposefully to find very distant objects that are highly magnified. And both MOSFIRE and Tom Sofa's new instrument, NIRES, with Keith Matthews, will look at objects which often are multiply imaged by these foreground clusters out to redshifts of 10 or so. These objects will have much higher signal to noise than the objects that we'll study with MOSFIRE because they will have this boost in magnitude from gravitational lensing. So let me summarize. I want to make 4 points. Keck Observatory has extended the frontier, I think, dramatically since the Blue Book in 1985. Astronomers are so much more reliable than politicians. We deliver much more than we said we would. Okay? It's provided unique insight into the nature of the cosmos through studies of dark matter, and there may be some interesting twists there. We've got back to the earliest 8% of cosmic history, but perhaps the most important thing is all of these projects involve graduate students. So imagine you're at the beginning of your career and you have the capability to make these fabulous discoveries. Thanks very much.